Hi everyone, I welcome you to my channel, The Chemist Chemistry. I'm your facilitator, Dozaman. In today's video lesson, I'd like you to stay tuned because we are going to talk about a very important question that baffles a lot of people when it comes to the concept of electron configuration. That is the configuration for chromium and copper. Chromium and copper. So I would like you to stay tuned. Don't close the video, watch it till the end, get the concepts well, and it's going to enrich your understanding when it comes to the electron configuration of the various atoms on the periodic table. So having gone through the various rules or principles governing electron configuration, we learn about Aufbau's principle, which says that orbitals of lower energy are first filled fully before those of higher energy. Now, so this diagram here represents or is a summary of what Aufbau was trying to say. So look at this. We have 1s orbital, which is the principal contour number 1. So you first have to fill the 1s orbital before the 2s. Then from there you come to the 2p. Then you move on to the 3x. From the 3s to the 3p to 4s. Then from the 4s you move to the 3d before 4p, in that order. So in other words, what this means is that 1s is low, the 1s orbital have a lower energy level than the 2s, and then the 2s also have a lower energy level than the 2p. The 2p also have a lower energy level than the 3s, in that order. So now today the discrepancy when it comes to the abnormality that chromium and copper is exhibiting when it comes to the electron configuration is within the 4s and the 3d orbitals. Now, looking at the 4s and the 3d orbitals respectively, you could see that the 3d is of higher energy than the 4s, even though the 3d orbital is in principal contour number 3, that is the third shell, and the 4s is in the fourth shell. So in terms of shell, the 4s is found within the fourth shell, and then the 3d is found in the third shell. So one may assume that because the 4s orbital is in a higher shell than the 3d, then the 4s orbital will have a higher energy level than the 3d, but that is not the case here. The 3d orbital, which is degenerate, is of a higher energy level than the 4s. If you want to understand all these things, below this video link or this video lesson, I have links where I have treated these principles already, so you can watch them in order to get the full understanding. So now let's move back to the first diagram. So now we have chromium here with atomic number 24. The chemical symbol is Cr. So the expected configuration should have been 1s, 2s, 2p6. So 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and then the 3d taking 4, in that order, because we are to fill the 4s before the 3d, since the 4s is of lower energy level. So the 4s must have a fully filled electrons. That is, the 4s is can take a maximum of what, 2 electrons, and it is of lower energy level. So according to Aufbau's principle, we have to fill the 4s. We must give it the 2 electrons before moving on to the 3D. But here, that is not the case for chromium. We must first give the 3D orbital 5 electrons before the 4s. That is where it does not obey the off-Bohr's principle or rule. And what is the reason for that? Because I have said it in the previous video lesson that, or in my previous video lesson, that half-filled orbitals are more stable than partially filled orbitals, and fully filled orbitals are also more stable than half-filled orbitals and also partially filled orbitals. So I want you to have it in mind. The most stable orbital is fully filled orbital. Then we have half-filled orbitals. Then the least in terms of stability is partially filled orbital. So what it means is that if a given orbital can accommodate a maximum of 10 electrons, and you give that orbital 9 electrons, it is not stable as giving it 5 electrons. Now, if you give it 5 electrons, 5 become half of the 10. So the 5 electrons make that orbital more stable than even giving it 9. And the one with 10, if the total electrons is 10, if you give it 10 electrons, it is more stable than giving it 5. But mind you that 5 is more stable than 9, than 8, than 7, than 6, than 4, than 3, than 2, and 1. Take note of that. So any orbital that take a maximum of 10 electrons, the d orbital accumulates a maximum of 10 electrons, and it is more stable when it is having 5 electrons than any other number of electrons apart from 10. So fully filled orbitals are more stable than half-filled orbitals, and then half-filled orbitals are also more stable than partially filled orbital. I want you to take note of that. So chromium exhibits extra stability associated with half-filled d orbital. So in other words, though by the time that the electron will reach the 4s and the 3d orbital respectively, it left with only 6 electrons for the chromium atom. So what happened is that because chromium exhibits extra stability associated with half-filled d orbital, the d orbital can take a maximum of 10. So half will be 5. So you have to give 5 electrons to the d orbital. Then the remaining one you give it to the 4s. Not that you are to give the 2 first to the 4s before giving the remaining 4 to the 3d, which is the expected configuration. But that one is wrong for chromium. So chromium exhibits extra stability associated with half-filled d orbital. So the d orbital must should be half-filled. In other words, half of 10 is 5. So you have to give 5 electrons to the d orbital. Then the remaining one must be given to the 4s orbital. And that is the observed configuration for chromium. Take note, for only chromium. So for the transition element, when we pick the first transition element starting from scandium to zinc, that is the first transition element, start from the element on the 21st, element, the element with the 21st atomic number, that is scandium, to the 30th, which is zinc. These series form the first transition series on the periodic table of elements. Yes, from scandium to zinc, they form the first transition element. So now what you should take note of is that among them, it is only chromium that exhibits extra stability associated with half-filled d orbital. So mind you, so when you are filling the configuration of chromium, I've taught you how to write the electron configuration of a given element, or let's say an atom of an element. So make sure for chromium you give the 3d orbital 5 electrons, and the remaining you give it to the 4s. Take note of that. Then for copper also have another abnormality or discrepancy. Copper also have extra stability associated with fully filled d orbital. So instead of giving the 4s orbital 2 and then the remaining 9 giving it to the 3d, that is not the case here for copper. Copper is saying that he preferred to have a fully filled d orbital because that is what will make it more stable. So you have to give the 3d orbital 10 electrons first, then the remaining 1 electron you give it to the 4s orbital, not like the actual way that you are to give the 4s 2 electrons before the 3d. No. So that is the discrepancy or the abnormality in the first transition series, that is between chromium and copper. Chromium exhibits extra stability associated with half-filled d orbital, and then copper exhibits extra stability associated with fully filled d orbital. So this will be the end of this lesson. I will encourage you to stay tuned for more video lessons, and your knowledge and understanding about chemistry as a subject will be enriched. Stay blessed, and don't forget to subscribe, comment, and like it.